Okay, so in the previous class, we discussed about two things. Both these two things were asked in today's class. One was to start with from the Reynolds transport theorem and to then derive the integral form of the mass conservation equation and the integral form of the momentum conservation equation. Okay, so these were the two things that we have done, and we see from today's quiz that it is reasonably straightforward to be able to obtain. Once you have the Reynolds transport theorem, you can easily obtain these integral equations by essentially putting n is equal to m and eta is equal to 1 for the mass conservation case, and eta n is equal to p or momentum mv, and eta as simply v, and then you have the momentum conservation equation, and essentially everything else is given to you. You just need to make these two substitutions and you get your momentum conservation and your mass conservation and momentum conservation equations. We also applied this equation to the wake survey method, and we said that if you want to find out what is the drag of an object, what we need to do is traverse with the probe behind the body or in the wake region, and knowing the velocity distribution, we can then find out the drag which is going to be acting on this, assuming that our control volume is large enough. Okay, so that means that we need to traverse over a reasonably large distance so that we get into the free stream on the other side, so that then we can apply, and then we have to be sufficiently far downstream of the body, so that then we apply, we can apply this and these equations, and we get, I mean, these equations are always applicable, but then lot of terms in the equations can be neglected, as we talked about in the previous class, and you have a very simple expression for drag, which was essentially related by u u infinity, let us say 1 minus u by u infinity, and the integral of this quantity with respect to y is what we need to evaluate in order to find out what is the drag which is acting on this object per unit length and so on, right. I mean, there are some constants like rho, etc., sitting somewhere, but so those are, I mean, one can check and put those. But so that's the essence of what we have talked about as far as the wake survey method goes. And we emphasized a few things that when you apply, look at this problem and any other problem, we should always apply the mass conservation equation first. Okay, so the mass conservation equation tells us, for example, in the wake survey method, that whatever mass is coming in from the left side is not going out from the right hand side. So there is a difference in the two mass flow rates, and the difference is what is going out from the lateral sides. And as the mass flow goes out from the lateral sides also, there would be certain momentum that it is going to carry with that, and that momentum has to be accounted for in the momentum equation. So unless and until you do your mass balance first and correctly, you will not get your momentum balance correct. Okay, so this is one thing which was very clear from the example that we took last time. Right. The other thing that we talked about is deformation of a fluid element. We said that there are two ways to look at this problem. One, where we say that, okay, we take a small element and we have velocity uv at certain corner, at a given corner, and then we can find out, using this information, we can find out what is the velocity at other points or other corners of that triangle. So that is one which is a purely mathematical description, that this is how the various points are moving. Now, because of the flow which is there, and the flow can have in general gradients. So the velocity at the 2 points A and B will not necessarily be the same. Okay, and we can write out using Taylor's series, if I know the velocity at A, what is the velocity at point B. Okay, and so this is a purely mathematical description. And then we said that in general, an element can only deform in 4 ways. One is pure translation, the other one is dilation, the third one is rotation, and the fourth one is a shear. Okay, so then we identify, so we can see that when it comes to the translation and dilation, it is, we can easily identify what terms are there where, whereas the other two terms is what we need related to our rotation plus shear. Okay, so I hope that this idea was clear, right. So we said that this is physical picture, this is a mathematical expression, both of them should be the same, and therefore we can simply equate the two. Okay, and by equating, we get an expression for how does the deformation or the shearing, what is my gamma xy, okay, which was essentially, we saw something like gamma xy was do u do y plus do v do x, and we saw that, or gamma dot we had written it with, and we said omega z was half of do v do x minus do u do y. Okay, so this is what we had gotten after equating, or essentially comparing the physical picture with mathematical picture. So this is one way to explain it, as we said, just to understand why when we talk about deformation, why do we get these two terms? Where do these terms come from? Okay, similarly, when we talk about rotation, how do these two terms come about? Okay, so then for a simple example or a simple case, we can see it, and then we say that, okay, the same thing is then generalized into 3D. Okay, so this is what we have looked at in the previous class. So we have looked at the integral form, and all of that is done, whatever we wanted to do. There is something on energy which is not really required for this course, but it is good to know that, and therefore we have given that as a homework problem. So make sure that you spend enough time completing this homework. It is substantially more difficult than whatever you solved in the as homework number 1. Okay, so please spend enough time on it. Now, and then what we are now trying to get to is the differential form of the equations, for which we have already introduced how the deformation of a fluid element would be. Now, in today's class, we will be introducing the idea of stresses, okay, and then we will talk about how do these stresses get related to my strain or strain rate. And in between, we will also realize where we start making assumptions, where does, till now we have not said what is the nature of the fluid. Okay, so the fluid could be, or the, so there are two things we can talk about: fluid being Newtonian or non-Newtonian, which we have not really introduced, although at one point of time when we talked about viscosity, we said that there's a linear relationship. We were sort of defining viscosity at that point of time. Okay, but we have not really defined Newtonian and non-Newtonian fluid, or where exactly do they come into our equation, is we have not yet said anything. What we have said in the integral is essentially exact. Okay, there is no, as you can see now, you can appreciate why and where we are bringing in the approximation. So here we have not brought in any approximation. You can say that this is something which should be applicable to any type of fluid. We have also not introduced whether the flow is compressible or incompressible. Okay, so we will see where does that get introduced. Okay, so these things will become clear as we will do the derivation now. So any questions before starting? Any questions from the previous class? Yes. There is no shape change in translation. Yes. So we are just saying that, okay, so that's a good question. So what we are saying is, why are we putting translation under deformation? So what we are saying is that any fluid element can deform, or let us say can do 4 things. Okay, there are 4 physical ways in which once it moves, things can happen. One is pure translation, where there is no deformation. So you can say that is a special case of deformation being 0. Okay, then we have that even pure rotation, there is no deformation as such, right? It's just rotating, the entire thing is rotating about some axis. Okay, but the other 2 cases where the area element increases, which is dilation, as we said, or where is there shearing. So in both these 2 cases, the elements are distorting. Any other question? Yeah. So we said that since the viscous force is coming from the wall pushing it, so we are assuming that our wall are very far away from the body that we are considering. But the control volume that we have taken, there are fluid present in the control volume, and the internal fluid friction is there. Why are we considering? Yeah, so we are not saying anything to do with the wall. We are simply saying that with respect to the lateral sides. Okay, so if you remember, we said that there is an object which is immersed in the flow. Okay, and then this is my control volume, and on this control volume, I am looking at what are the forces. So we are looking at the shear force which is acting on this lateral sides. So these are the shear forces which are acting on this control volume, and this shear force multiplied by this area and sum it up on and then add up on both the sides, that will be the shear force which is acting on my on this control volume, right? Now we said that if I look at the velocity distribution, somebody was talking about boundary layer. We can think about it in boundary layer terms or whatever. So the thing is that if I look at how does the velocity distribute itself or gets distributed here, so you can see that there is a gradient which could be called as a boundary layer, and then later on there are no gradients essentially. Okay, so we get into the free stream region. Okay, so when we go to the free stream region, you can see that the gradients, so this shear stress that we are looking at is a primarily gradient of u component of velocity along the y direction, okay, which is now becoming 0. So that's why we need to take a large enough control volume so that these stresses become 0. I mean, this is all approximations in some sense, because you can say that, okay, they are never 0, they will always be gradients, etc. One can keep on arguing, which is probably right. I mean, we are not really, but to a very good approximation, we can make them as 0 as far as these these control volume is large enough. That's why we said that to be able to throw away these shear forces, we need in the lateral direction the control volume to be large enough. Okay. Now we also said that there is a pressure force, and this pressure force to vanish, we need the control volume along the longitudinal side, along the flow direction, to be much large, very large. Okay, so that we can say whatever is pressure on the upstream phase has now become the same as the on the downstream, or rather the pressure on the downstream phase has now become the same as the pressure which was on the upstream. Upstream is anyway the undisturbed, should be the undisturbed part, and therefore the two pressures are the same, and therefore there is no net pressure force which is acting on this object. Okay, so that is why we need a large enough control volume for these approximations to apply to work. And that also means that when we are actually measuring the velocity, we need to measure all the way to a large lateral direction. Practically, that's what it means. And it means that we have to measure large enough, because there we are not really plotting any control volume, drawing any control volume. We are simply measuring certain things in the wake. Now, where should we measure? That's why we said we should measure sufficiently far downstream. Okay, and we should go all the way as far as possible, sufficiently into the free stream on both the sides. Okay, so that these assumptions are now getting satisfied. Okay. Any other question? So total momentum is manifesting as drag, right? Okay, so whether it's an addition or a subtraction, okay, so that you can see that now. So in fact, you have the integral form of the equation, right? So there you are already putting in the velocity terms, and it will automatically come out whatever is the velocity. So we saw that there is a net outflow from the sides, okay, and then it is if you look at the lateral sides, they are essentially going to flow along this direction. So they are going to carry a positive u with them, okay, because we have said that this is my x direction, this is my y direction, positive x direction. So the velocity component which is along the positive x direction is my u, positive velocity component along the positive y direction is my v. Okay, so this is a positive u that you are going to have, and the momentum, the mass that is going out is also positive, because whatever is entering here is not leaving on the other side, less is leaving on this side. Okay, because of this, because of the wake region, there is a, so that means that the remaining has to go from the sides. Okay, so it's going to carry momentum along with itself. So the more, for example, mass like this you allow it to move out, the contribution of these terms are going to be much larger. And you can see that this contribution I cannot make it as 0 by even making any size of control volume. Okay, because again, because of the imbalance in mass on the two sides. But what we can do is simply assign that this velocity is u, the free stream velocity. Okay, that's what we are doing. Whatever mass is going out, we are assigning it as a velocity capital U, because we are assuming that this control volume is, this phase is far away from this body. If it was not, then we will have to bother about what is the local velocity that I would have there. Okay, and that's why the size of the control volume, as we said, the drag force is the same, but the other forces will keep on changing if you draw a different size of the control volume. But ultimately, you will get the drag force to be the same. And of course, the momentum term on the left hand side is also changing. Okay, momentum balance is changing, forces are changing, but your drag force should remain constant, because that's the physical, that's the only physical force that is constant in all this in the problem, right? Right. Or maybe we have written it this way: u square u times 1 minus, or capital U minus u. Right. Yeah, there is no need for an extra u square here now. Right. Yeah. So now how is it coming? So we just said that you are doing the integral. I mean, I have showed you the various steps, right? This small u is the local velocity. This is what is being measured here. So here you are measuring u as a function of y. Okay, this is my capital U, and this capital U is anyway invariant. So these are the velocity components which are involved here. Okay, so we have done the derivation. Okay, so please go back and look at the derivation. If you're not clear, we can talk about it offline, because this is something we have done, and there is no conceptual thing that I need to explain here. You just need to look at the maths again. Any other question? Okay, so if there are no more questions, we can get started with today's lecture. So we will start off by the idea of stress. So this idea is known. I'm sure everybody knows about stress, but there are certain subtleties that we need to understand better. Okay, so that's why this should be still useful. And if not, let us say that that's a repeat. Okay, it's a small part which is getting repeated for. Okay, so how do we define stress? So let us say we use a symbol sigma, and we say it is force upon area, right? So the first thing that we realize, so if I talk in terms of scalar and vector, so what sort of a quantity we are looking at for force? Force is a vector. What about area? Is a scalar or vector? Vector, right? So that means when we talk about two, when we are looking at the ratio of two, so that means that there is a direction which is associated with area. There is also a direction which is associated with force. So that means that the stress should now have two directions, one which is corresponding to the direction of the area, and the other one which is going to correspond to the direction of the force. So if I look at stress at a point, so let us say that this is my point, and we are just looking at the various sides of this. Let us say that this is my x direction, this is my y direction. So on this face, so what face is this? So how will I define this face? So there is an area, right? And of course, everything is perpendicular. I mean, there is a z direction, which is unity in this case. So this area is so when we say area, how do we define the area? By the normal, okay, by the normal element. Okay, so what is normal to this element here? So this is along the x direction, right? So now you can have force which is along this direction, or you can have force which is along the other direction, right? So you can see that I can now get two different type of stress components. Okay, so we will call this as sigma xx, and we will call this as sigma xy, where we are using the convention that the first, what is the first subscript referring to here? This is related to the normal to the area. So this is related to area, the face. So normal, this is area to area element. and the other one is corresponding to the direction of force, right? Everybody clear about this? Why we are putting two subscripts? Now let us look at this face. What is this face? This face is oriented along the minus x direction. Okay, so if I want to have a positive stress, you can see here area element is now in the negative x direction. So I should apply force in the negative x direction so that my stress now becomes positive. Okay, so I can see that this is how I will apply this stress here, and on the other side, when I look at this, I will apply it like this. Y direction, it has to be negative so that the stress becomes positive, right? So these are also my sigma xx term and sigma xy term. Everybody clear? Now what about this face? This is a positive y, okay? So then we can apply forces along the positive y direction, and that will lead to sigma yy, and I need to apply force along the positive x direction, okay? So which is going to be along this direction here. So this is now going to become, what is this component? Sigma yx or xy, yx, because the face on which it is applied is y and the force is along the x direction. So this is my sigma yx. Similarly, on the bottom face, this is my sigma yy, and this is going to be this element is, let us say that this element is now sigma yx. Okay, everybody clear how we are just defining stress? Now the next thing is to show that sigma xy is equal to sigma yx. Okay, by the way, sometimes when it comes to, so we can say that these are my normal. Sigma xx, it is very clear, is my normal stress, and sigma xy is my shear stress that is happening, correct? This is also very clear. Now when we talk about, so sometimes we also use a convention, we sometimes also write tau xy, okay, for shear. So we can continue using sigmas for normal and tau for shear. Okay, so I'm just telling you that again, I may be using both these two symbols interchangeably. Okay, but so either you can alert me or you can just make a note that this is what it means. Okay, now how do I show that these two stress components are the same? We can just take a moment. Okay, you can take a moment about this point. Okay, if I take moment about this point, okay, you know that these normal forces are not going to contribute anything because there is no moment arm that I have. There is a force, but there is no moment arm that I have. So these will go to 0. Okay, what I will be left with are essentially these stresses. Okay, and that has to be equated to not 0. Okay, because there is a torque, it should be equated to I alpha, moment of inertia times your angular acceleration. In general, you can have your element can accelerate, right? And here we are talking about a torque. We need to equate it to the angular. Everything has to be angular now, right? So we'll have to equate it to the angular acceleration that we would have, and of course multiplied by the moment of inertia I of this element about this axis here. So if you write it out, you can show that I mean, this is elementary, so therefore, I mean, I just introduced the idea of stress, and I'm reminding you why the stress tensor is symmetric. Okay, clear? Now, if I were to write it out in 3D, what will I have? I will have sigma xx, sigma xy, and I will get sigma xz. Okay, so that will get added, and similarly it will get added here. So if I want to look at sigma, okay, I would have sigma xx, I have sigma xy, I have sigma xz, and then we have sigma yx, sigma yy, sigma yz, then sigma zx, sigma zy, and sigma zz. So this is what my stress tensor. We have not introduced tensor yet, but we will do it formally in a later class. But this is my stress tensor, that's what I get. Okay. So all I have done is collected all the components that are there. Okay, we have introduced the components where they are coming from. Okay, first in 2D, and then we said that we can generalize it to 3D, and we introduce these extra terms in there. Otherwise, in 2D, you will only have these 4 components. In 3D, you will have these 9 components in total. Any questions here before moving ahead?
So we can write the 2D also as a tensor, right?
Yeah. So right now we can see that there are how many elements are there? 9 elements. So this has 9 elements. And we have also said that it is symmetric, okay, because of symmetry. How many elements do we get? We get 6 independent elements, because all these stress terms are going to be the same. Okay, and these are the same now. Okay, so I get only 6 independent stress elements from here. Okay, everybody clear? So this is a very quickly a recap of stresses, which as I said, I'm sure you know about it. Somebody who's seeing it for the first time, please raise your hand. You're seeing it for the first time? Okay, fine. So any questions here? This is clear? Okay, so here you have to understand that we are talking about force per unit area, and when we look at any element, we have to look at the direction of the area, and we have to look at direction of the force. Okay, so those, I mean, who are doing it for the first time, for you, it may, because this is not a trivial concept. Okay, so we will have to, I'm just repeating myself there, and therefore we call this a sigma xx, sigma xy. You can also have sigma xz. Okay, and then we saw that how go from right side to the left side, and then similarly we went into the top side, and we use the convention that the first subscript is going to give me the normal to the area element, and the other one is going to give me the direction of the force. Okay, but thankfully we have symmetry. Okay, so sometimes we are not carefully, and we can also write this as sigma xy, etc., etc. We can keep on interchanging, because we know that in the ordinary conditions, that the stress tensor is symmetric, and we need not worry about the order in which we put these subscripts. Okay. So now let us look at, so stress was anyway an intermittent quantity. Ultimately, what we are interested in is force. Okay, so we are interested in force, and therefore we will now we will see how to define the force from here, and what is it that we get. Okay, first let us say sigma was just used as a definition. Sigma is F by A. That was just used as a definition. But now we need to know what is the force that is going to act on this area element. So we will do that once very quickly, so that there are no gaps in our understanding. So if I of a fluid element. So if I now want to look at, of course, force as a vector. So let us say if I want to find out force. So let us say I give you this and I ask you to what is the force along the x direction. So how would I find out the force along the x direction? So you have to multiply each stresses now. This is the state of stress that we have. And from this, we have to find out what is the force. So you have to take each element. So what are the things which can contribute to force along the x direction? Sigma xx, okay, on the right face, sigma xx on the left face, okay. Then you have sigma yx on the top face, okay, and sigma xy on the bottom face. Okay, so all these four stress terms can lead to force along the x direction, right? Yes, no? So please give me the expression quickly. So you have sigma xx. We start off with a simple sigma xx and sigma xx multiplied by the area element. Let us say this area element is delta x and delta y. So it's going to be delta x times 1. Okay, so where is the sigma xx acting? So sigma xx is acting on this element. So this is actually delta y. I have written it incorrectly. So this is going to be delta x and this is delta y. So sigma xx is acting on this element, which is delta y times 1. Okay, similarly, if I look at whatever is happening on the left side, okay, we have sigma, same thing, sigma xx into delta y into 1. Okay, plus sigma yx, this is acting on which phase? What area is it acting? Delta x into 1. Okay, and from the bottom side, we have sigma, okay, I think again, yeah, sigma yx into delta x into 1. Okay, so I'm just showing you how to write an expression of force once we know the stresses. Okay, so this is the expression of force that I would get. Right? Yeah.
So how do we physically measure the stress on a fluid element?
How do we measure? We say there is no direct way to measure a stress. Normally, we would measure the force and divided by the area. Okay, it's like energy, it's like entropy. It is there's no direct measurement of them. You can only infer it by measuring certain other quantities and then calculating it from there. Okay, any other question? Okay, so now what it is clear, so what is the force that I will get on this element? As of now, we are saying that it is 0. Okay, so if I have to make it non-zero, okay, so now, I mean, this is all introduction now. Now we will start getting to what is of interest to us. So how do I make the force non-zero? That the two stresses which are acting on it are not the same. Okay, so that means that I'm now talking about an element or a point which is here, and there is a small gradient. So the stresses which are acting on this, on a small distance, which is, let us say, at the distance of delta x by 2, this distance is delta x upon 2. So here now the stress that will be sigma xx. So if the stress here is sigma xx, so here the stress will be sigma xx plus, how will I find out the stress here? Again, do a Taylor series expansion. Okay, again it is going to be the gradient of sigma xx along the x direction. So dou sigma xx dou x and multiplied by this increment, which is delta x upon 2. So this is what is the stress. If the stress at this point, at the center point, is sigma xx, then the stress at this point on this phase is going to be given in this manner here. right? Understood? And the stress on this side is going to be sigma xx minus the same thing but with a minus sign, dou sigma xx dou x and delta x upon 2, right? And because we are only doing it in xx, I'm not going to look at the other terms. We are just going to look at these 4 stress terms which are contributing to force along the x direction. And how much is this? So this is my sigma yx. Okay, sigma yx was here. So what is here? Sigma yx plus derivative of this quantity sigma yx with respect to what direction? Y direction. We are moving in the y direction, so y, and multiplied by the increment. How much is the increment? Delta y upon 2. Good. What about the bottom face? Same thing with a minus sign. So it's going to be sigma yx minus derivative or dou sigma yx dou y times delta y upon 2. Right? So now if I find out this force on this element, what is the force along this element? So I'm not going to write out the expression once more. This is the same expression. Instead of sigma xx, you have to substitute this and so on, right? So what will I get? So this term, you can see that this term, as we saw in the previous case, these two terms are going to cancel each other. And this part is what is going to remain, okay, because this is coming with a positive sign here, and this is going to coming with a negative sign here. So these two will again add up. So I will get force as dou sigma xx dou x into delta x plus dou sigma yx dou y times delta y into the area is already here into the area component, you are right. So the area would be multiplied by delta y, and that is actually important because then you can see that this two, so delta x is going to come from here, okay, and then sorry, or let us say for this sigma, this delta y is coming from here and delta x is going to come because of these two difference, or if you want you can just write it out fully. And so let us just write it out. So fx is equal to sigma xx plus dou sigma xx dou x delta x upon 2 multiplied by delta y into 1. Okay, so what we have done is this stress we have substituted here, okay, and of course the area element is not changing, so that remains unchanged. Okay, minus, now instead of this stress which is there on the left hand side, this has to be the, we need to put this stress. So sigma xx minus dou sigma xx dou x delta x upon 2 times delta y into 1 plus sigma yx plus sigma yx dou y delta y by 2 times delta x into 1 minus sigma yx minus dou sigma yx upon dou x delta x upon 2. Sorry that we are running out of space here. This is delta y here, this is delta y here. This is delta y and this is y. Multiplied by delta x into 1. Okay, so now you can see that this sigma xx is cancelling out. This is also cancelling out. Okay, and these two terms are now adding up to give us that the force that I get now so the force I will get now is going to be given as dou sigma xx dou x delta x into delta y, okay, plus dou sigma yx dou y delta x into delta y. So there are two interesting observations that one can make from here. What are these? One, these stresses do not lead to force. What leads to force? Net force. I mean, of course, they lead to force, but net force, the gradient. Okay. So it's only the gradient in stresses which lead to a net force. The stresses will lead to a force, but they will balance out. So if you want to have a net force, then you need to apply a gradient. That's the first thing that will come out, that is coming out. Okay, that's why we wrote the first expression, we showed that is 0. So if the two stresses are the same, we are getting exactly 0. So only because when we get these stresses, these gradients, then we get it as non-zero. Right? The other thing which is coming out, interestingly, is this term is now common between the two of them. So if I look at force per unit area, okay, so if I divide everything by this quantity, you can see that those two terms are readily addable now with a common term which is delta x into delta y, which is essentially the area of this element here. Okay, and this is like a common theme that you will see, and that is makes our life much easier that way. Okay, and of course, if you were to do it in 3D, you will get instead of 1, everything is multiplied by 1 here. This 1 will become delta z, and that will get carried. So this will become delta x into delta y into delta z. So essentially, it becomes a volume element. Okay, is this clear? Now, at this stage, we will just pause and tell us that, okay, what type of force we are looking at. So we are going to now think about 3 types of forces, which we have introduced at some stage, but we will now formally introduce it. So we are going to talk about a force which is acting on the entire body, which we'll call it as a body force, just like our gravity is acting on every element of my body and is pulling it down. Okay, so that's my body force. The second force, which is acting only on the surface, okay, so that we will call it as a surface force, and the third one we will call that as a line force. Okay, so think of L cubed. So body force is like will scale as L cubed. Okay, it's like volume, it is scaling as volume. The other one is going to scale with surface area, so it's an L square force, and therefore there should be some L force as well, which is my surface tension force. So we have these 3 types of forces. So gravity, and if you are applying like an electric field or a magnetic field, and if there's a charge, the fluid is charged and you are applying an electric field to that, then the entire fluid, all elements in that fluid will start experiencing that force. So it is experiencing inside, I mean every element or wherever the charge is present, all that is going to respond to that electric field that you have applied, right? So it's a body force. Okay, so there have been several examples of body forces other than gravity that we can think about. Okay, now when it comes to surface force, then surface force is acting on the surface. So pressure, viscous, etc., etc. These are all going to be acting on the surface. So there are several examples of surface forces as well. Okay, now when it comes to line force, the only line force that we have is surface tension. Okay, so now if I look at this element, which one are we talking about here? So this force that I'm talking about, this is acting on the surface of this object. It is not acting everywhere. So I will call this as a surface force. So this is a surface force term that I have now written. Okay, everybody clear about this? So if I want to denote it further, I can say this is my F, S, and along the x direction. Just to now emphasize this fact that I am talking about as a surface force. Okay, as we saw that this is only acting on the face of this element that we have. So what will be a body force? How will I write a body force? So we are right now looking at forces. So we are looking at body force along the x direction. So I will write it out with, let us say, FB is my body force. And then this body force has to be multiplied by the volume. Okay, or maybe sometimes we define it per unit mass. So this is essentially like an acceleration, although we don't call it as an acceleration, we think of it as a body force. So we have to now multiply it by mass. So what is my mass now? Is rho times delta x into delta y, okay, multiplied by 1 in this case. Okay, it will be delta z in general for a 3D element. We are talking about a 2D element, so we have multiplied by 1. Okay, any questions here? So what we have done very quickly is to introduce the idea of stress. Okay, we have also introduced or shown how do we get forces from there. Okay, and we have also said that to have a net force acting on a fluid element, we need to there need to be a gradient in stresses. Otherwise, we will have a force, but there will be a no net force that I would have. Okay. Then we I have introduced very quickly introduced the idea of a body force. Okay, and line force will never enter the equation directly, so we will not introduce how to write a body force. Sorry, a line force. Okay, so this is sort of the basic now. What we will do, so we have all the basic elements with us. Now we are ready to actually drive our uh, uh, mass conservation equation in differential form and the momentum conservation equation in differential form. So we have all the elements. So these were like deformation of the fluid element and the stresses that we have introduced. They are all like background material that we would need to actually plug in into these sort of, in intermittent equations. We will see where exactly we will need them. So I will get rid of this and start from continuity equation. So which is conservation of mass. This is also a conservation of mass equation as applied to a differential element. So earlier we were talking about a finite size control volume. Now we are talking about an infinitesimally small control volume or a differential element. So let us say that there is some flow which is happening. Let us say I choose a small element here, and again everything we are doing in 2D. We can as well do it in 3D. It's just that we get more complicated. It just becomes more difficult to imagine and so on. But once we have the results, we can see that it is very easily generalizable from here to 3D. So once we understand that this is a process, we can then go back and see that, okay, in the derivation, what did we miss out by not including the z direction, variation along the z direction, and then we can readily include those terms. Okay, so it's a much simpler approach that way. So again, if this is my x direction, this is my y direction. So I have to now look at in this element, what will I use? What will I get? How will I start applying it now? I have to figure out how much mass is coming in, how much mass is going out, and how much accumulation is happening in this control in this region. So again, I'm going to go back to my accumulation is equal to growth plus influx minus efflux. Okay, so we can go back to the same idea. We know that for when we apply mass, this growth is 0. Okay, we have already discussed this. Okay, we have also said that it is non-zero. I mean, we can think of it as non-zero if it is a phase change or it's a chemical reaction or it's a nuclear reaction. Okay, so and we said that we are not really talking about these cases, so we are going to drop this term. So what is my influx? So I will now start writing out or showing. Okay, by the way, maybe I have gone too fast. Any questions here? Anybody has a doubt with whatever we have said? So let us say that this is my velocity rho. Which component of velocity will make it enter? The v component of velocity. Okay, and here what will make it enter? Mass enter rho times u. I mean, rho, whatever fluid is coming in here has density rho, and it is coming with the velocity u. Okay, and so if I look at the influx, what is my influx? Is velocity, which is v, multiplied by this area element. Okay, this is my delta x. Okay, so v into delta x into 1. Okay, so that is what is how much mass, how much volume is entering into 1. This is my area element multiplied by velocity will give me the volume element. The volume which is entering multiplied by rho will give me how much mass is entering. Okay. Now what is leaving on the other side? Again, we can go with a small element. This is a small thing that we have. So we can find out readily from Taylor series. So rho v will be here, and the derivative which will be there plus, I mean, you can take a derivative of each of them. So v will become, let us say, v dv dy times delta y. Right? This is how my v will become. And similarly, my rho will also become in a similar way, rho d rho dy times delta y. Okay. So this is the this is the density that I would have on the other interface. Okay, of course I can combine them. If I can think of it as rho v, then this is nothing but same thing into y times delta y. I mean, just multiplying these two terms, I will get this term, and the other term is like a higher order term, so I don't have to worry about it. Okay, similarly, what is living on the other side, I can write it out in a similar way as rho u plus rho u, sorry, dou u rho u to x times delta x. So my efflux term is, okay, so influx I have not written it completely. So influx was this one velocity component rho v multiplied with this area, plus this is also bringing in the mass, so I have to write out that term also. So it's rho u times delta y into 1, correct? And efflux is rho v, which is going out. Okay, and we said that we are just going to combine it like this, dou y rho v times delta y times delta x into 1 plus rho u plus derivative of rho u along the x direction times delta x, and this is leaving through a phase delta y into 1. Okay, everybody with me? So we can see that we have found out in this equation the influx term, growth is anyway 0. So I have to now worry about my accumulation term. How will I write out the accumulation term? First, accumulation term is going to be written with what sort of a derivative? Time derivative, and whether it will be d or dou. Dou is a partial derivative, right? Because we are talking about the accumulation part, not the growth part. The growth term is written with a d and accumulation is written with a dou. We have seen and argued that. So I get accumulation term accumulation is equal to whatever is the mass which is there, which is rho times delta x into delta y into 1, that is my volume. This is my volume, and multiplied by rho gives me the mass which is contained in this volume element, and then I take a derivative with respect to time, partial derivative with respect to time, okay, and that becomes my accumulation term, right? So now we have everything, and we can now put in all these terms that we have found into the equation that we have, okay, and what we get, okay, so you can see that these two terms, this term is going to cancel out, similarly this term is going to cancel out, okay, and from, so putting in Reynolds transport theorem, we are still calling this statement that we have written as Reynolds transport theorem. So if I put everything in the Reynolds transport theorem, the left hand side is dou by dou t of rho delta x delta y times 1, and the right hand side is equal to dou by dou y of rho v times delta y times delta x times 1 plus dou by dou x times rho u times delta x into delta y into 1. And we have to realize that efflux is with a negative sign, and this is the net efflux that we are going to have. Correct? So this is the equation that I get, and of course I can now realize that delta x delta y into 1 is common, so that can be dropped out. So I just cancel out this term. Okay, and anyway, this volume is not changing with time. We are just thinking of that element is fixed, like our Eulerian frame of reference. We are keeping that element as fixed with time, and therefore this is simply taken out. And I get dou by dou t of rho plus, I'm now going to bring everything, all the terms on one side. So rho u dou x plus rho v dou y. Now if I can write out, and this is equal to 0, and if I can now see that if I were to extend this whole thing in 3D, okay, nothing really changes other than I will get one term. So the mass, so you can see that the accumulation term is not going to change, okay, other than this one can be then substituted with delta z, okay, and these area elements will also have, instead of 1 will have get delta z, but in the efflux term there will be one more extra term that I would get, okay, which will correspond to, which will be w dou rho w dou z. Okay, so I can then generalize. So I'm now not just writing it, so add it in 3D. In 3D, this term will also appear. Okay, this 2D to 3D business, I'm just doing it a little bit more quickly. You can go back and convince yourself that we are not really missing out anything. Okay, so it's reasonably straightforward, but for you to have fundamental clarity, you need to sit down on it with it, okay, for a few minutes and make sure that you're not going to, you're really not missing out anything extra. Okay, you need to convince yourself. Just don't take my words. Sit down and convince yourself. See where the changes would be, what changes would be, and then show that this is all that you would get. Okay. Any questions here? So this is our continuity equation in general form. This is my general form of the continuity equation. We are going to derive a few special cases from here, especially the case of incompressible flows, and maybe we'll discuss that in the next time. We will let us go to the next equation that you would like to try. Okay, any questions here again before we move ahead? Okay, now when we go to this equation, we will see that a lot of things that we have talked about in the past, all of them, a lot of them will be required here to do this derivation of momentum. And this is the most celebrated equation, which is known as the Navier-Stokes equation, and this is going to be in differential form. We are just making this distinction because we have already derived our conservation of momentum in the integral form, starting from the Reynolds transport theorem. So we will start off by saying that we have force is equal to mass times acceleration. So is equal to force, okay, or maybe you can start off by saying that the change in momentum with time is equal to the force. This is the basic definition of force that we have. This is Newton's law, coming from Newton's law. And we have said that we are not taking the case where the mass is varying with time. Okay. So we said that those are the cases which are corresponding to phase change or reactions or thermal or nuclear reactions. So otherwise, these are the only ways, and therefore we are not considering those cases. So I will write out this equation as this form here is equal to the force which is acting on it. Okay. Now we are also going to say that the force, we have already differentiated it and said that the type of forces that we have are body force and surface tension or surface forces. Okay, so this is my body force. So all these external forces, which could be of only three types as we have discussed: body force type, surface force type, or a line force type. And we said that line force will not enter our equation, so we are not going to write it down. So this is my body force. This is my surface force, not surface tension force. This is surface force. Okay. So we are going to just write out the expressions for these. So first of all, what do we see from the left hand side? How can we write out the expand out the left hand side? Yeah, Reynolds transport theorem, or maybe the material and the local derivative, we have derived a relationship between them. We are going to say that the mass of this element, we have been drawing this element, delta x, delta y. What is the mass of that? Is rho delta x, delta y times 1. This is the mass. And this derivative, we are going to write it out as dou u dou t plus u dot del of u. Okay, so what we have done now is, if you recall, that d by dt was dou by dou t plus u dot del, right? Essentially, this was our u dou by dou x plus v dou by dou y, and in scalar form, this is what it was. If I write it out in vector notation, then this is what I would get, right? So that's all we are doing now. We are using this relationship and expanding out the left hand side, and the left hand side is nothing but this term that we see here. Okay. Any questions here? So again, instead of doing it in vector form, which may be confusing, I can see that there are some people who are not looking very comfortable to me. So let us do it only for the x direction, and then we will see how to do it for the other components, and then we can add up everything in a vector form or write it out in a vector form as required. So only for x, so for x direction, here I have not drawn explicitly the x, y area element, etc. We have drawn it enough number of times, so we know what we're talking about. So I'm going to write out rho times delta x times delta y into 1 as earlier, and here we are only talking about the u component of velocity. And from here, I'm also expanding out this u dot del term, and this is nothing but u dou by dou x plus v dou by dou y, and let us say that we do it only in 2D, okay, just to keep things simple for now, and then we can expand it out if need be. Okay, so again, I mean, so now you can see that all we are writing is actually this equation. Okay, we are only writing Newton's law of motion into a form that is of relevance to us. Okay, this is not very useful. We said that why was it not useful? Let us very quickly recall what was the main argument. And this goes back to our argument of Eulerian and Lagrangian description. Okay, we said that because we have decided not to move with the fluid element, we have decided that I will stay at a given point. So I'm going to describe everything in a Eulerian frame of reference. Okay, so therefore I will now have to write out this derivative in this form here. If I don't do that, if I want to move with the fluid element, this is good enough. I can keep moving with the fluid element as if I have a ball which I am throwing, and I can find out what are the frictional forces and what are the gravitational forces and everything, buoyancy force and everything else which is acting on it. I just write out all the forces on the right hand side, and I equate it to mass times mass times acceleration on the left hand side, and that is good enough. That's all. Okay, so we are only applying this equation, but now we are saying that, and that's why all this basic, as we said, whatever we have discussed till now becomes relevant. Okay, we said that we don't want to do that, and we have discussed why, and we have said that very quickly that because we cannot follow so many fluid elements, okay, therefore we have decided that I'm going to stay at a point. I'm going to, it's like in a train analogy, we said we are going to stay at a station rather than move with the train, because how many such trains can we move and so on. So we decide to stay at a point, and we are going to do a description with respect to that. And therefore, this acceleration that we have is now being written in this manner here. Okay, understood? Now, when we look at forces, again we have given you the expressions for the body force and the surface forces. So what was my body force? It is F body force times rho times delta x times delta y into 1. We have just written this, you can recheck your notes. And what was my surface force? That was dou sigma xx, dou x plus dou sigma yx dou y times delta x into delta y into 1. Okay, that 1 we had not carried explicitly, but we can carry forward that 1, and this 1 is going to appear here as well. Okay, so everybody clear? So we can see that we are now getting towards the so-called the Navier-Stokes equation. This is now appearing like, this is the first equation that we have. And of course, here what we realize is that I can take out this delta x, delta y, delta into one term. This term is common, so I can remove that. Okay, so now we can see that every term that we talk about in Navier-Stokes, we go with after removing this delta x, delta y into delta z term or into one term. So everything that we are talking about is per unit volume. Okay, so let's keep that in mind. So because so everything that we look at is per unit volume. So don't forget that. So when we have to actually get to the force, total force, we will have to multiply it back by the volume of that element. Okay, here everything is cancelling out. That's why it is not appearing. But of course, but nonetheless, each term is now per unit volume term. Okay, so if you look at this equation, this is also a very important equation. I can write. I'm not writing it out in a cleaner form without this term. Okay, or maybe let's just do that. So I am just removing and keeping rho from here. I am removing this term, and this is now becoming a rho times FB term, and this term is gone. So this is also a very important equation that we have, and this equation is what is known as a Cauchy's equation. And you know how to generalize it to 3D. In 3D, what will happen? What will happen? You will get an extra term, which is going to be sigma zx, derivative of that with respect to z. That is one term that will get added here. And here I have to add a w dou by dou z term as well here. Okay. Other than that, we have everything with us. Correct. And again, as I said, going from 2D to 3D, it may not be, you may not be that comfortable. Okay, this may look like, oh, what is happening here? So maybe please go back and look at the notes and convince yourself, as we have said, about these things. So what we understand here is, if I now look at the momentum equation, so what were the physical principles on which we are finding out our conservation equation, conservation laws? Okay, so you can say that this was based on mass conservation or basic idea of Reynolds transport theorem, which are essentially the same. We have already motivated from where it comes. The momentum conservation equation is also coming from the Newton's law. Okay, and at this stage, this is all that I can write out. Okay, so this is where I essentially have to pause. I cannot proceed with anything that I know in the past. Okay, everything that I know in the past has been utilized to write out this Cauchy's equation, right? So whatever we have talked about has been used. Eulerian Lagrangian description has been used, and the idea of forces, body force, etc., all that has been used in terms of stresses, that has been used, and then I'm able to write out this equation. Okay, but if I look here, pause and find out what we have, how many variables, how many equations that we have. Okay, what is it that we get? What are the variables here? Maybe you can start discussing that. What are the variables in this equation? What is it that we do not know and we need to find out? So look at this equation. Do we know rho? No. Yes. Density could vary in the flow. Okay, so density is a variable. Okay, so density is a variable. U, V, and W are in fact variables. Okay, so you can see that I have 4 variables from this equation. Okay, now if I look at this equation, what variables do I have? Okay, I've already counted rho and U and V and W, so I'm not going to count that. This is a body force which is typically given to you externally. This is gravity or whatever body force if it is given. Okay, now if I look at sigmas, you can see that sigmas are not known. Okay, and how many sigmas do we have? In 2D, we saw that there are 4 stress terms, and because of symmetry, I will be left with 3. In 3D, I know that I will have 9 elements, and because of symmetry, that will reduce to 6. Okay, so you can see that the number of variables that I have, if I count the number of variables turns out to be 6 stress elements and 3 velocity elements and 1 density. So I'm talking about 10 elements as of now. And how many equations do we have? 2, and of course, you can write out similar equations for force along the y direction, force along the z direction. So then I would have 3 momentum equations, okay, because momentum is a vector quantity, so I can write out in 3 components for that. So I have 3 momentum balance equations and I have 1 mass balance equation. So how many equations do we have? 4. So you can see that I have 4 equations and I have 10 unknowns with me. Okay, and this is right now the problem of closure. This is one thing, I'm just pointing it out. The other thing which you see now which is missing, anything which is missing from whatever we have discussed here, any variable which is missing? Pressure. So we have not yet introduced the idea of pressure yet. Okay, make a note of that. We have not yet introduced the idea of pressure. So pressure is going to come through the stress terms. So these stress terms are going to be dependent on pressure. Okay, so that's where we will have to bring in pressure. Okay, but as of now, what we have said is that we have 10 variables and we have only 4 equations. Okay, so our system is actually not closed. Okay, so we will come back in the next class and we will see how to tackle this problem.